Hello everybody and welcome to the Carlem Cymru revision sessions. The session this evening will focus on comparing electric, magnetic and gravitational fields and will be presented by Jane Owen from Penglai School in Aberystwyth. The session will last around 45 minutes where Jane will run through the relevant content. If you have any questions during the session, then please use the question and answer section within the live event and we will do our best to answer. The session will be recorded and the recording and any relevant resources will be uploaded to the e-sgol website under the Carlem Cymru tab. And with that then, Jane, over to you.
Thank you very much, James. Okay, and yes, I'm going to attempt to look at fields, forces, potential, and potential energy for electric fields and gravitational fields. And I'm also going to pull in magnetic fields. So let's always start with forces before we go on to fields, okay? And electric forces are dependent on the charges, whereas gravitational forces are dependent on the masses. Magnetic forces on a current, the force is proportional to the current. So if we look at currents and if we look at charges, the force is proportional to the charge. But that's not all. Okay, so let's just have a look at the force for electric fields. And the force, like gravitational, is proportional to the inverse of the radius square. All right, in both cases. So we call this the inverse square law. And it's much like a light bulb shedding out its light, and it will do it radially and it gets dimmer further away, and it's the same with the force. From a point charge or a point mass, the force will radially get weaker and weaker further out. In fact, we can put all of this together into an equation. So the force is equal to 1/4 pi epsilon naught, the charges Q1, Q2 over R squared, where this quantity here, 1/4 pi epsilon naught, is called the proportionality constant. Now we can succinctly kind of like reduce that a little bit, and we can just call it K. And we can just say that it's 9 times 10 to the 9 per farad meter. All right, so we could write it like this: F equals K, Q1, Q2 over R squared. So the force is proportional to both of the charges, whether they're positive or negative, and the square of the distance, the inverse of the square of the distance. And if we take a charge, Q1, all right, Q1, and we take from that, let's say it's a positive charge, and we take from that the R from that Q1 source charge, then if we have another Q2, then if it's a negative charge, for example, then that would be attracted, and you can see that the force would be in the opposite direction to the radius or the distance from the source charge. So we call this the source charge Q1. Q2 here would be the test charge. And because the force is attractive, positive and negatives attract, then that means that the force will be negative force. Whereas if it was a positive charge, it would repel, then that force would be in the same direction. Let's put a little positive here. All right, Q2. And then the force would be in the same direction as R. So that's why it would be positive. Okay, all right. So if it's attractive, it will be negative, and if it's repulsive, it will be positive. Let's do exactly the same thing for the masses. So for the masses, the force for the gravitational force, the force is dependent on the value of the masses. So the force can be written as G, m1, that's our source mass, m2, divided by r squared, where G here is our proportional or proportionality constant. And that is given to you, proportionality, yeah, constant. And that's given to you in your data booklet, 6.67 times 10 to the minus 11 Newton meter squared kilogram minus 1. Now that can only ever be attractive. So you've got your test mass M1. The R goes from that source mass. The R goes from that mass. And if you put another M2 close by, then the force will always be attracted to M1. And because it's in the opposite direction, we say that the force is negative. And it's only ever attractive. Okay, so we can see with the gravitational and with the electrical, it depends on both of the charges, both of the masses, and the inverse of the square of the distance between those. All right, now let's have a look at magnetic while we're here for forces. Now the force depends on, for currents, the force depends on the current. The force also depends on the length of the conductor put into the magnetic field, and it also depends on the magnetic field strength B. Okay, magnetic field strength. Okay, and in fact we can put all of those together to give you F equals BIL. We call it BIL, BIL. Usually it's given by a little l, BIL. All right, and so the proportionality constant there is 1. All right, so they don't, nothing is just straight force is proportional to BIL, and because the proportionality constant is 1, it just comes out as F equals BIL. Equally, we can do the same for force on a charge moving in a magnetic field. The force is proportional to the charge. The force is also proportional to the speed with which that charge is moving. So that's your velocity, not to be confused here with voltage at all. It's a small v. And the force is also proportional to the magnetic field strength that it's traveling through. And so we can also write here F equals B Q V, and for an electron we can say F equals B E V, i.e. BeV. So we often talk about BIL and BeV for the force of either a charge or a current placed in a magnetic field. Okay, so now we've looked at forces, we now need to kind of explain. Now, before I move on, we've got to remember that forces is a vector quantity. It has a direction as well as a size. And that direction could be positive or negative. All right. Now, if we are adding at all forces, we've got to consider the fact that they've got this size and we've got this direction. So we have to resolve any components into suitable directions, right angles to one another. So we have to resolve into components. All right, and that is often the difficulty. It's no good just adding the size up. We can't do that. We have to add the components that are in the same direction. All right, okay, so now let's move on to fields. Okay, now with fields, Okay, let's have a look at what that means. Okay, now for an electric field, what it means is it's the force per unit charge. Whereas for gravity, what it means is it's the force per unit mass. Okay, so it just depends on what what field it is. So for electric, you've got the force per unit charge. So it's the charge that's experiencing that force. Okay, so that experiences a force in an electric field. And we say that we can write it like this. So E, the electric field, E, is given by force per unit charge. Whereas for and so the units of that would be newtons per coulomb. Gravity, on the other hand, would be, again, force per unit charge. So we can say, and we use little g for this, okay, because big G is gravitational constant, is given by force per unit mass. And that will be units of G would be given newtons per kilogram, like that. Okay, and that is a mass that experiences a force when it's placed in a gravitational field. Okay, and we might as well look at magnetic while we're here. So the magnetic field is given by B, measured in Teslas, and it acts on a current when it's put into the magnetic field. So it's the current that experiences the force in a magnetic field. Okay, and we'll be looking at a long wire and a solenoid. Okay, and I'll come back to that. So let's have a look at two charges. We have to pretend that we are putting a tiny little test charge in the field of a charged particle. So this is our source charge here, which is creating the electric field around it. If I put a positive charge anywhere near it, it would want to repel. So I draw my lines outwards as though that there was a little positive charge on those lines, and which direction would it be going in? And in this case, they'll be all going outwards. And you'll notice that as I'm drawing this, I'm drawing it so that all of these field lines are at right angles to the surface of my source charge. It's as though they appear to come from dead center. All right, and they immerse from the surface at right angles. Okay, so I'm just going to pop here that remind ourselves that E, a little bit complicated because E is very often used for energy, but here E, capital E, is used as an electric field strength, and that's defined as the force per unit charge, newtons per coulomb. Okay, all right. Now, if we had a negative charge and we put a little positive charge next to it, which direction would it be moving in? It would be attracted. So all arrows would be coming towards the surface, and it hits it at right angles to that surface. All right, so it's always good to kind of like do, you know, your 4 north, south, east and west, and then halfway in between. And you can see that the electric field gets weaker further away because the field lines are further apart. And the closer they are together to the source, the stronger the field is. So we already know that the force is given by K. I'm not going to put 1 over 4 pi epsilon naught. I'm just going to use K here now. Q1, Q2 over r squared. But Since we know the electric field strength is the force per unit charge, if we divide it by Q, i.e. divide it by Q2 to give us the electric field strength, it cancels out and we just get K Q1 over R squared. All right, so this in a sense is my test charge that I've put into that field that experiences a force. This Q1 here is the source charge that gives you that electric field in the first place. So we have to take into account the signs again, and very often you'll see a little bracket with a negative in front of that equation. Because whether it's attractive or repulsive. Remember, it's again negative for attractive and positive for repulsive. And for the same reason that the force was, i.e. you take the distance r from the first source mass or first source charge, and the force is in the opposite direction if it's attractive, and if it's in the same direction and further out, it'll be repulsive. Okay, but also it's worth remembering here for electric fields that E for two parallel plates, its potential divided by the distance between those two plates. And this is for two parallel plates. So this comes up in capacitance, and it sneaks itself in because it's another equation for electric field strength that you might forget. So we've got the top one here, all right, and we've also got a second one. Now let's go over to gravitational fields. Now there's two ways of looking at gravitational fields. If you look on kind of like a local level, then the G, we say that the gravitational field is uniform. Because if we're looking at on the surface of the Earth, all of those field lines are parallel, and that's why we say it's uniform. Whereas if we look at it and we say that there's Earth and we look at it on a much bigger scale, then we are putting our test mass nearby. What happens to it? It wants to be attracted towards the Earth. And so wherever we put it, it's going to be attracted towards the Earth. And so all lines point to the Earth, okay, to give us a field that is changing. So G, little g, gravitational field strength will be much, much stronger closer to the Earth and much weaker further out because the field lines are further apart. All right, so we can look at, so we know that G equals force divided by mass, mass being the test mass that you put into the field by the source mass. And we can say that F equals G m1 m2 over r squared. So if we want to find what G is, we divide that by mass, that's m2, and we can cancel out so that we get G equals G m1 over r squared. So notice the field is still an inverse square law. It still obeys that, i.e. the further out it gets, the weaker it gets. And it's dependent on the mass in gravitational fields, and it's dependent on the source charge for the electric fields. Let's have a look at your current in a magnetic field, and using our right-hand grip rule, I don't know if you use that right-hand grip rule. If you've got your right hand, it'll curl around, the magnetic field direction will curl around if you point your thumb in the direction of the current. So if you like, this will go all the way around like this. Okay, use your right-hand grip rule to determine the direction of that magnetic field. And actually, these get a lot further apart, the further out that you go. So I'm just going to use a different colour to distinguish. This is the distance from the current, and this is given by A. And so the B field, magnetic field, is proportional to 1 over the distance from the current. Notice it's not an inverse square, but it is an inverse radial, but it's not an inverse square law. And also B is also proportional to the current flowing through the wire. In fact, one of your equations is B equals mu over 2 pi I over A. All right, so this is our constant of proportionality. Okay, constant of proportionality. I'll leave it like that. Okay, and then if we have a look at a solenoid, again, we can still use the right-hand grip rule. And this time, if you curl your fingers around in the direction of the current, the thumb points north. All right, so this end in this direction will be north, this end will be south. And we can draw our field around our solenoid with a current passing through it. Okay, and north to south, and then it goes in the opposite direction inside. But if you just have as a rule of thumb, if you curl your fingers around in the direction of the current in the coils, the thumb points north. Okay, so that end of the coil will be north, and then everything else will follow. So in this case, the magnetic field is proportional to the current, and it's also proportional to the number of turns per unit length. So this is the number of turns per unit length. And we can put all of that together. So B, the magnetic field, is equal to mu naught N I. So again, mu naught here is my constant of proportionality. Okay, so I think now this mu naught here in your data booklets is given by 4 pi times 10 to the minus 7 Henry per meter, and it's the permittivity of free space. Okay, and I think I'm going to park magnetic fields because I want to go on. So we've done forces now, we've done fields. Now I want to go on to potential. And I'm going to park magnetic fields to one side and just look at potentials. Before we move on though, remember fields is a vector quantity. It's a vector quantity, so it's got positive or negative signage. All right, the field is the area, just to recap, it's the area where something experiences a force. Okay, experiences a force. So that would be a mass in a gravitational field, it would be a charge in an electric field, it will be a current in a magnetic field. Okay, and if you're adding, if you're having to add, again, you're having to consider, all right, your direction and your size. So you're going to have to resolve it into two components that are right angles to one another and then add them. All right, you can't add them unless they're in the same direction. Okay, let's go on to potential. All right, now potential is given by V. All right, now this is a lot easier than forces and fields because it is a scalar quantity, which means that we can just add all right, don't have to consider direction with this. In fact, it's a little bit easier. Now, I'm going to put subscript E for electric potential and subscript G for gravitational potential. And electric potential is given by joule per coulomb, and gravitational potential is given by joule per kilogram. Okay. Right, okay, so what is it? So for electric potential, it's the work done in bringing unit charge from infinity to that point in the field. Okay, so it's been given by, so if you've got E for the electric field, and if you times it by the distance, i.e. we've got E is the force per unit charge, and we times it by the distance, that gives us the electric potential. All right, whereas in gravitational, it is the work done in bringing unit mass from infinity to that point in the gravitational field. So that's given by, so Vg will be given by the gravitational field strength times by R. Well, we have an expression. So let's start from basics. I always like to start from basics because you've got the force is K Q1 Q2 over R squared. If you can just remember that one, everything else will follow. All right. Now, if we then, to get the potential, it's the work done. So we want the force per unit charge. So that's KQ1 Q2 over R squared divided by Q2 times by R, the distance from that source. So charges cancel, R's cancel, and you have KQ1 over R. Okay, and that is for the electric potential. Okay, right, and that and the units are joules per coulomb. And we can do exactly the same thing for the gravitational force. F equals G m1 m2 over R squared. And the gravitational potential is the work done in bringing unit mass from infinity to that point. So we want the gravitational field, the force per unit mass, so G m1 m2 over R squared m2, and then times it by R, and that cancels. The R's cancels, the m2's cancels, so you're left with G m1 over R equals the potential, the gravitational potential. Okay, perhaps I've rushed that little bit and I've made two jumps. I've made the jump from the force to the electric field, and I've jumped then from the electric field to the potential. All right. Okay, so if I have got, let me just show you what I'm meaning. If I have in at the center, I've got Earth. Okay, and if I've got on the very outside, we say far away from the Earth, we say that the potential there at infinity is equal to Vg equals to 0. So if you are here on Earth, or and actually the closer that you go towards Earth, you're getting the gravitational potential is getting more negative. So if you're on Earth, you have to give it potential in order to reach 0, because it's like looking at it as a potential well. All right, and looking at it that you just give it enough energy just to get out to the outside. So my colleague was explaining me before, you kick a football and you up a hill, and just as it gets up to the top of the hill and it just stops, that is where the potential is 0. And then we're down at the bottom of that hill where the potential is negative. So we call it like a negative potential well. So you have to give it energy to get out and up to the top, and that's like at infinity where the potential is 0. Okay, and okay, anything else I want to include? Okay, so let's move on. Let's move on to potential energy. Now, potential energy, like potential, is scalar. So thank goodness, we don't have to resolve any components. So it's only got a size. So we can add it quite happily, or take if you want to find the difference, but you don't have to worry about the direction at all. Now, potential energy, how is that different to potential? Well, potential energy is work done. It's the force times by the distance. It's the, and we're going to look at it in terms of the electric and the gravitational potential energy. So the okay, so potential energy, change in potential energy is given by the charge Q times by the change in potential. Okay, so what we say is the work done. This potential here is the work done per unit charge. So all we have to do is times it by the charge to give you, so if you times it by the charge, it gives you the energy or the work done. And the work done is the same thing as the energy. All right, and that is given by in joules. So potential energy, all of it will be in joules, whether it be gravitational or electric. So let's do the same thing for gravitational potential energy. So the change in potential energy will be given by the mass times by the change in gravitational potential. Okay, and again, that will be in joules. So you're doing the same thing. This is the work done, all right, per unit mass. Per unit mass. And if you times it by the mass, it gives you the potential energy. Okay, so this kind of like, you might see this equation in this form, E, but for energy this time, not for electric strength. So I'll put that as energy here, equals QV. And you might have seen this very often, where energy units, if it's an electron moving, are in electron volts. Okay, and that's where that comes from. Again, if you've got a positive source, no, I won't do that. I want to show you a couple of things. I'm looking at the time and thinking, have I got time for a past paper question as well? I have got one prepared for you. So let's have a look. So potentials, have a look at this. VE is the electric potential, 2, 4, and 6. So if this is a positive charge, and I've got a positive charge here, you're going to go increasingly more closer. So you're gaining in potential energy. Is this right? So you're going to have closer. So the closer you get, you're going to have a gain in potential energy as you go in. So gain in potential energy. Okay, between the positive and the positive. Right, now, because you're actually having to do work, aren't you? You've got two charges that are the same value, are the same charge, and you're having to do work in order to kind of like push them together. Okay, so let's have a look at the graphs situation, because you do need to know about that. So if you have got a graph of potential, electric potential against R, you'll get this sort of relationship, and the gradient here is given by, and you'd have to take a tangent to that at whatever point. You'd have to take a tangent, you'd have to draw a straight line, you'd have to draw a triangle, and the gradient of that is given by VE divided by R, which is equal to the electric field strength. But if you have electric field against R, and again, you'll have a relationship that looks like that. What we do here is we look at the area underneath the graph, and the area is equal to that electric potential. Now, if we look at it in terms of the gravitational and the masses, so if we have gravitational potential against R, and it's always going to be attractive in any case, so we're going to have this sort of relationship, i.e. it's going to be negative, all right, in the opposite direction to what R is taken. And we say, again, take a point wherever you need to take the gradient, draw the triangle, and minus Vg over R is equal to the gravitational field strength. Whereas if we look at the what do I want to say? I don't want to say that. What is that? I'm meaning G, aren't I? I'm meaning G here. Gravitational field against R, and I look at the area underneath, i.e. between the line and the axes, that will give you the area, and that's equal to the potential, gravitational potential. Okay, I think I've done enough there in terms of going over all of the different potential energies, the work done, the potential, i.e. the work done in bringing unit charge or unit mass from infinity to that point, fields, i.e. looking at the area where that and whatever experience of force in that area around either the mass or the charge, and also looking at the forces in the field. So we've had a good look at that. Now in WJC, they give you this table, and they really want you to kind of like be able to compare. So the fields between electric fields and gravitational fields. And it's only one small thing to then jump onto the magnetic fields, and we have done that. Okay, and I've given you here all of the kind of the specification, but I want to have a look. I think I've got just about time to do some practical work, because for all of these fields there's a couple of specified practicals that they are expected you to have experience with. So this is a Hall probe going into a solenoid, and they've given you a relationship there, B equals mu naught Ni, which we've covered. And you've plotted here B against I. And we have to relate that to Y equals mx plus C. So they've plotted B on the y-axis and I on the x-axis. So that means the gradient is given by mu naught n, where n is the number of turns per unit length. So we've got this graph here, and they've added in error bars. You can see that there's two good lines included in all of the error bars, and they straddle 0, 0 here. So the first part of the question here is calculate the mean value of the gradient. So in order to do that, we have to identify our triangles that we are going to use. So we can use and do them as big as possible, and do them with a ruler. So here it will be, and write on it what the actual numbers are going to be to work out the gradient. So 60 here, down to 0 here, 2.95, and then here would be 0.1. Okay, so it would be 60 divided by 2.95 minus 0.1. If you actually show your read-offs, they can't take the marks away from you. They will be checking the read-offs to check that you can read it to the nearest half a square. So once you've done it for that gradient, i.e. your steepest one, then you can do it for the shallowest one. So again, another big a triangle. Again, write on very clearly what it would be. So that would be 56, and this is coming up to 4. So 56 take 4 divided by 3 take 0. Okay, and that will be giving you the gradient, the shallowest gradient. To work out the mean value of the gradient, then add them up and divide by 2 to get the mean gradient. To get the percentage uncertainty, get that, find what the difference is. Okay, so m dash minus m dash dash, i.e. the steepest minus the shallowest, and then divide it by 2, because you've got to come up with a plus minus figure. And then you can divide that by the mean uncertainty and times by 100% to get the percentage uncertainty. And leave your answer to 1 or 2 significant figures. All right. Have a look at it and see what you think it should be. Okay, if it starts with a 1, I say 2 significant figures, but just have a look to see. Sometimes it's easier to leave it as 2 significant figures, because when you come to the absolute uncertainty, you can then round it to 1 significant figure then. Part B, calculate the number of turns in the solenoid. So the gradient, as we have seen up here, is given by mu naught n. So mu naught is given to you as 4 pi times 10 to the minus 7, which is 1.26 times 10 to the minus 6. Okay, but you have to remember that n is big N, the number of turns per unit length. So big N divided by L. So if we put that in for n, and that's equal to the gradient divided by mu naught, we can rearrange it to get n. And the percentage uncertainty in our gradient, we can use that and add it to the percentage uncertainty in our length to get the percentage uncertainty in the final value of the number of turns. So whatever we had up here, we can add it into it. I think this comes up to about, I can't remember. And I haven't got enough time to actually physically work it out. I thought I would. Okay, so then whatever the value is, I've got the answers here. So whatever the value is, and they say the value, if you do all of that, is say 3,780. Okay, that's the value of n. Okay, I've included a mark scheme underneath. All right, plus or minus 400. Okay, so they've used, they followed it through. Now, it says there, it says whether or not the graph is in agreement with the equation. So what they're asking is this number close to the 5,000 that it should be? Well, actually, it's not close. So it doesn't matter if it's inside or outside, but you can say that the 5,000 is not within the range, and therefore it is not in agreement with it. But equally, you could look at the graph and say, well, the straight lines are going through all of the error bars, and the straight lines are straddling the origin. So in that sense, you have got this relationship B is proportional to mu naught Ni. There is agreement. So to one extent, it's not accurate because it's not within range, but it is in agreement with the equation because they are straight lines. They do all pass through the error bars, and it does straddle the origin. Okay, right. Well, I've also included another, because, you know, I've done all of this theory, but don't forget, they do like to include, even in the theory papers, they do like to include, you know, practical analysis. So I've left the mark scheme because I thought I might not quite make it. I've left the analysis there. I've left the mark scheme there to go with very simple experiment. Again, force against current here. Again, error bar analysis. And even though you're expected to do that for your practical in your data analysis, don't park it, because it comes up in your theory papers, this kind of like expectation to relate the graphs or equations to y equals mx or y equals mx plus c, and relate it to, you know, the findings. All right, discuss whether, you know, F equals Bill, you know, is valid, you know, and you've got to relate it to your graph, whether the lines all pass through the error bars, whether the lines straddle the origin, whether, you know, and comparing the values. Well, I think that is a fitting finish, because we've tried to go over a couple of questions. We've looked at the potential energy, the work done. We've looked at potential, i.e. the work done in bringing unit charge or mass from infinity to that point. We've looked at fields for gravity, electric and magnetic. And finally, we looked at forces. And what I would say is, always start with the forces and build from there. Thank you very much for listening. I hope that's been of use, and over to you, James.
Thank you, Jane. I hope you found today's session useful. Tomorrow's session will be an ASH session, and it will be focusing on the nature of waves, or if you like, wave basics. That's an ASX session. And then next week, then, what sessions have we got lined up then?
We've done capacitors, we've done fields. You're doing vibrations.
I'll be doing vibrations, that's right.
That's it.
Yeah, okay. Well, thank you and goodbye, everyone.